Hello everyone. Now we'll see some properties of convergence in probability. We already know that almost sure convergence implies convergence in probability, and if we have convergence in probability for a monotone sequence of random variable, then that sequence converges almost surely also. So these two things we already know. Now we'll see further properties. Before that, let us just revise the definition of convergence in probability. So we say that a sequence of random variables xn converges in probability to a random variable x if probability of mod xn minus x being less than epsilon goes to 1 as n goes to infinity, or the other way, probability of mod xn minus x being greater than epsilon goes to 0 as n goes to infinity. Okay, so set of all omegas for which mod xn minus x is less than omega, it goes on increasing as n goes to infinity, and it reaches a stage where it has probability 1. So it is a big enough set. Okay. Now about properties. So we already stated two properties. Now let me state the third. So if xn converges to x in probability, this is the notation, then there exists at least one subsequence of xn which converges to x almost surely. Okay, so there exists at least one subsequence which converges almost surely. Okay, now we won't go into the proof of this result. There are further interesting properties. So before that, let us see one example for convergence in probability. So let xn be a sequence of normal random variables with mean 1 by n and variance also 1 by n. Okay, so mean and variance both are 1 by n. Then what can we say about probability of mod xn being greater than epsilon? Why am I interested in this? Because since mean is going to 0 and variance is also going to 0, probably xn is going to a degenerate random variable, degenerate at 0. Right? Can you intuitively picture this? Mean is going to 0 and variance is also decreasing. So entire mass is probably going to get concentrated around 0. Hence, we are trying to see whether xn minus 0 goes to 0. Okay, so we are considering this. Now we can use Chebyshev inequality. Chebyshev inequality tells me that this probability will be less than or equal to expectation of xn square upon epsilon square, right? And what do I know about expectation of xn square? Expectation of xn square would be variance of xn plus mean of xn square. So 1 by n plus 1 by n square, and we know that this goes to 0 as n goes to infinity. Okay, so a larger sequence goes to 0, and of course being probability this is non-negative, hence by sandwich lemma this also goes to 0. So what we have is if xn converges, if xn has distribution normal 1 by n 1 by n, then xn converges to a degenerate random variable, degenerate at 0. Okay, in probability. Now you must have realized that here we are using Chebyshev inequality, but for using Chebyshev inequality we used some result about expectation of xn square. So we use the fact that expectation of xn square is going to 0. Okay. In general also we can use Markov inequality and rth moment. Hence we have another important result. Convergence in rth mean implies convergence in probability. Okay, convergence in rth mean implies convergence in probability. So let us try to give a proof. It's very small proof. So what is given to me is xn converges to xn rth mean for some r greater than 0. Okay, this is given to me. Now we have to check convergence in probability. So as I mentioned, we would use Markov inequality. Markov inequality tells me probability of mod xn minus x being greater than epsilon is less than or equal to expectation of mod xn minus x raised to r upon epsilon raised to r for a fixed r. Okay. Now since xn converges to xn rth mean, using this we have expectation of mod xn minus x raised to r goes to 0 for that particular r. As a result, this larger sequence goes to 0 and hence probability of mod xn minus x being greater than epsilon also must go to 0 because it is always non-negative. Okay, and this is nothing but convergence in probability. Hence, convergence in probability is a weaker condition, whereas convergence in rth mean is a stronger condition. So if rth mean convergence happens, then convergence in probability is automatically true. Okay. We can have one more example. Suppose xn is a sequence of random variables, discrete random variables, and it takes only two values, 1 and n. Let us say it takes value n with probability 1 by n and it takes value 1 with remaining probability. So with probability 1 minus 1 by n. So the larger value has very less probability of happening as n increases. Okay. So important point to be noted, xn's are not identically distributed. Every xn has in fact a different support also. Not just probabilities are different, even the support is different. For x1 is degenerate. For x2 support is 1 and 2. For x3 support is 1 and 3 and so on. Okay. And now as we can see 1 by n goes to 0. That's why probably entire mass of xn is going to converge to 1. So xn is probably going to converge to a degenerate random variable, degenerate at 1. Let us try to examine. So probability of mod xn minus 1 being less than epsilon, if I try to compute, then this probability, see, if xn is equal to 1, then of course this is going to be 0 and hence it is less than epsilon. Okay, so this probability is going to be greater than or equal to probability of xn is equal to 1, because xn equal to 1 automatically implies this. In addition to that, if epsilon is large, there may be some more omegas for which it happens. Okay, and probability of xn equal to 1 is 1 minus 1 by n. So it goes to 1 as n goes to infinity. Hence we have probability convergence. So xn converges to a degenerate random variable 1 in probability. Okay. It is not necessary to have limiting random variable as degenerate. You can find some non-degenerate random variables also. So that is your homework. Give an example of convergence in probability where the limiting random variable is not degenerate. Okay. Now, if you remember, for almost sure convergence, we had one condition, one criterion which we could use to check almost sure convergence easily. In fact, we stated two such criteria. So for probability convergence also we are going to state one such criterion. So xn converges to 0 in probability if and only if expectation of mod xn upon 1 plus mod xn goes to 0 as n goes to infinity. Okay. So we have if and only if means the condition is necessary as well as sufficient. If xn converges to 0, then this thing happens, and if we can prove that expectation of this quantity goes to 0, then xn converges to 0 in probability. Okay, this is an important criterion. It can be used to check convergence in probability. Let me state another important result. If xn converges to 0 in probability and if y is any real random variable, then y into xn also converges to 0 in probability. Okay, y into xn also converges to 0. Now let me go one step ahead for next result. In almost sure convergence, we also studied convergence of continuous functions of random variable. So do we have something similar in probability? So the result that we are interested in is if xn converges to x in probability and if g is a continuous function, then can we say that gxn converges to gx in probability? So this is in fact true. If xn converges to x in probability, then gxn converges to gx in probability. Okay, this result also holds. Another important thing is algebra of sequences. So if I have xn converging to x in probability and yn converging to y in probability, can I say that xn plus or minus yn converges to x plus or minus y? Then xn into yn converges to x into y, of course in probability, and xn by yn converges to x by y, provided yn and y are not 0. So all these things are also true. Let us try to prove for addition. Other things follow almost similarly. So what I want to see is probability of xn plus yn minus x plus y being less than epsilon. Does it go to 0? Does it go to 1? Okay. So this would be probability of mod xn plus yn minus x minus y less than epsilon. So this would be probability of mod xn minus x plus yn minus y less than epsilon. Okay. What we know is mod of xn minus x plus yn minus y is less than or equal to mod xn minus x plus mod yn minus y, triangle inequality. Okay. We also know that xn converges to x in probability. So probability of mod xn minus x being greater than epsilon, this goes to 0, and probability of mod yn minus y being greater than epsilon, this goes to 0. Okay. So we will make use of these results. The same thing can hold even if I write epsilon by 2 here. Now I am interested in computing probability of xn minus x plus yn minus y being greater than epsilon. Okay. So if this is greater than epsilon, then of course this is also going to be greater than epsilon because it is further greater. So this probability is greater than or equal to probability of mod xn minus x plus mod yn minus y being greater than epsilon. Okay so far? because this is anyway smaller. So if this is larger than epsilon, this has to be larger than epsilon. And if the addition is greater than epsilon, then at least one of the probabilities must be greater than, at least one of the numbers must be greater than epsilon by 2, because then only addition can be greater than epsilon. If both of them are less than epsilon by 2, then we can't have addition greater than epsilon. So what we know is probability of mod xn minus x being greater than epsilon by 2 goes to 0. Probability of mod yn minus y being epsilon greater than epsilon by 2 goes to 0. Okay. And addition greater than epsilon means at least one of them. So let me call this event as, say, an. Let me call this event as, say, bn. And we are interested in probability of an union bn. Probability of an union bn would be probability of an plus probability of bn minus probability of an intersection bn. So I can say this is less than or equal to probability of an plus probability of bn. Okay. And we know probability of an goes to 0, probability of bn goes to 0. So probability of an union bn must also go to 0, because of course it is non-negative. Okay, probabilities are real numbers. So real sequences, by sandwich lemma I can say probability of an union bn must go to 0. Okay, hence probability of mod xn minus x plus mod yn minus y being greater than epsilon goes to 0, and hence the reverse probability, that is probability of mod xn minus x plus yn minus y being less than epsilon goes to 1. I have skipped one step here, going from this to this being greater than epsilon. Okay, but I think you can see it from the earlier discussion. Okay, so this is another important result, that is addition of two sequences which convergent probability converges to the addition of their limits. Same thing can be done for multiplication and product, multiplication and division. And you also have something like axn converging in probability to ax if xn converges to x in probability. Okay. So these are important results. We have not yet talked about uniqueness of the limit type of result. In almost sure convergence, we proved that the limit is unique almost surely. Do we have something similar in probability? So yes, we have something similar in probability also. If you have a sequence converging to two different limits, then that limit is actually unique almost surely. Let me state the result. So if xn converges to x in probability and xn converges to y in probability, then x is equal to y almost surely. Okay, you can't have two distinct limits. Let me try to prove that. Okay, so we can say probability of mod xn minus x being greater than epsilon by 2 goes to 0. Similarly, probability of mod xn minus y being greater than epsilon by 2 goes to 0. And we can use same argument like we did just now for addition. What we want is probability of mod x minus y being greater than epsilon. That can be written as probability of mod x minus xn plus xn minus y being greater than epsilon. And now this can again be simplified using triangle inequality, and this would go to 0. Okay, but because anyway it is free from n, going to 0 would actually mean being equal to 0, because this is free from n. Okay, so this going to 0 would imply that this is equal to 0. Hence x is equal to y almost surely. Okay, so the limit in case of convergence in probability is unique almost surely. Okay, we don't say x is equal to y in probability. There is nothing like that. X and y are equal almost surely. So probability convergence actually gives us almost all the properties that we would expect it to have. Okay. So we'll stop here. Thank you.